Okay, here's video 8 of our intersession video series, and it's on curve sketching and function analysis. I already highlighted this box, which means you're gonna have to highlight it too. So our guidelines for analyzing the function, or analyzing the graph of a function. First, find the domain and range, find any x and y intercepts, vertical and horizontal asymptotes, symmetry of graph. Find critical points and intervals where the function is increasing and decreasing, determine local max and min points, determine concavity and find points of inflection, and then lastly, sketch the curve. So let's get started. We have on example 1, we're given this function. First thing we got to do is take the derivative, which would be 3x squared minus 12x plus 9. We're going to have to set it equal to 0, but if you notice, all three terms are divisible by 3. So we can actually divide by 3, so that's x squared minus 4x plus 3. We can set this equal to 0, which would be easier. You can do tic-tac-toe, AC method, whichever method works best for you. X minus 3, x minus 1, set it equal to 0. Your critical points are x equals 3 and x equals 1. So we're going to jump down here where we've got already a sign chart. So our critical numbers are in order, 1 and 3. We need some values in between, and I just went with 0, 2, 4. Plugged in these values into the original function, not the original one, into the derivative function. And when it was 0, it was increasing. When it was 2, it was decreasing. And at 4, it was increasing again. So it went up, came down, went up. And then from here, we're going to go into our second derivative. So we have the first derivative, now we got to find the second derivative. And this one will be 6x minus 12. We can factor out a 6. X minus 2, set it equal to 0. So our point of inflection here is 2. We have a sign chart right underneath our first one. We're actually going to cross out this critical right in POI, because that's our point of inflection. Which in this case was 2. You need some numbers before 2 and after 2. Easy ones are 1 and 3. Substitute these values into the second derivative. Here, these values are negative. Here, these values are positive. So before 2, it's a concave down function. After 2, it's a concave up function. The function the original function is not a fraction, so we won't have any vertical asymptotes or any horizontal asymptotes. We know it's continuous because there are no restrictions, so if it's continuous, it'll be differentiable, which we already found the derivatives to. The domain and the range, no restrictions. So domain and range will be both negative infinity to positive infinity. And let's go from here. On our first derivative test, it went from increasing to decreasing, which means that at 1, we're going to have some type of maximum. So if we plug in 1 into the original function, this is really 1, 2. If we look at the second part, we went from decreasing to increasing. We're going to have a minimum here. If we take 3 and plug it into the original equation, we get 3 and negative 2. If we take our POI, plug it into the original function, we end up with 2, 0. So let's summarize before we continue, before we sketch our graph. Okay. To start off, we have a y-intercept at 0, negative 2. Our x-intercepts we're not going to worry too much about for the moment. We have a relative max at 1, 2. We have a relative minimum at 3, negative 2. We have the function increasing from negative infinity to 1 and from 3 to positive infinity. It's decreasing between 1 and 3. We know the domain from negative infinity to infinity. The range will also be from negative infinity to infinity. It is continuous and differentiable because it is a polynomial with no restrictions. And we have a point of inflection at 2, 0. So let's sketch this out. We have a y-intercept at 0, negative 2. And that's the point. 1, 2, 3, negative 2, and 2, 0. And the function is going from moving on to our next example. Well, now we have a fraction, which means we're going to have to find our VAs and our HAs. Remember that to find the VAs, you have to set the bottom equal to 0. So in this case, let me write this one up top. VA and that's x squared minus 9, set that equal to 0. It's a difference of squares, so you have a VA at 3 and another VA at negative 3. For your HAs, you have to look at the degrees of the top and the bottom. The degree here is 2, degree here is also 2, so you take the fraction of the leading coefficients, which in this case are both 1, so really your HA is just 1. There's your VA, there's your HA. The domain will be everything except these two values, and the range will be, I'm assuming, since we haven't done all the work yet, from below this value up to here, and then from this value above it. So, as far as x and y intercepts go, we won't have any. We will have a y-intercept if we substitute in our zeros for x's. We'll have a y-intercept of negative 1/9, so let's make sure we label that one. And let's see. Alright, let's move on to finding our... So first things first, we gotta find the derivative. And I know exactly how you feel, it's a quotient rule. So, low and high, and high, low, all of it, low. They both have a 2x in common, which we can factor out. We are left with x squared minus 9 minus x squared minus 1. And all of it still divided by x squared minus 9 squared. Our x squared will cancel out. The inside is a negative 10, so we really have negative 20x over x squared minus 9. So from here, we're going to take our critical point from the top, calling this critical number. From the bottom, we already know that our VAs are here, which means that our derivative will not exist in this bottom portion. So we know that our critical numbers, in this case, will just be 0. We'll have discontinuities at x equals 3 and negative 3. For our first derivative test, substitute all these values in, negative 3, 0, 3. We know that at 0 it would be 0, 3 won't exist, negative 3 won't exist either. And some values in between, so negative 4, negative 1. If we substitute in these values into the derivative function, we end up with increasing, decreasing, and decreasing. The only values that we do have any significant changes when it goes from a positive to a negative, which means this is a maximum. And we already know that that maximum is actually our y-intercept, which we had already found, 0 and negative 1/9. Okay. So from here, let's move on to the second derivative. Here's the simplified version of the first derivative. Let's move, again, we're going to have to do quotient rule. So let's move on to do second derivative, which will be low d high without the x minus high d low all of it over low low. Well, from here we can factor out a 20 and an x squared minus 9. And from here, we would set it equal to 0. However, we can't once again, we're going to summarize before we begin our graph. Let me see where we're gonna do this. Guess we'll do it down here right before our graph. Apologize for all the moving. I had to record these myself since George has to work. So we know it has a y-intercept at 0, -1/9. We know that a maximum, we don't know what kind of maximum yet, is also at this point. We know it has the VAs at x equals -3, at x equals 3. We know it has an HA, y equals 1. We know the domain of the function is from -infinity to -3, from -3 to 3, and from 3 to infinity. The range will be from -infinity to 1, and from 1 to infinity. It increases, where does it increase? From -infinity to -3, and from -3 to 0, decreases from 0 to 3, and from 3 to infinity. That's based off our first derivative test. It will be concave up from -infinity to -3, and from 3 to infinity. And it'll be concave down from -3 to 3. So let's sketch this out. So 1, 2, 3, got a VA. 1, 2, 3, got another VA. 1, you got an HA. That's y equals 1, x equals 3, x equals -3. That's 0, -1/9. And it's increasing from -infinity to -3, and it's also increasing, it decreases from 3 to infinity. It increases from -3 to 0, and it decreases from 0 to 3. And there's the graph. Now, hopefully with these two examples, that should be enough to help you guys complete example 3, which is all on that page, and the very last example. Now, given that we need to do a lot more writing in all of our classes, you guys already have the answer key to all of these notes. So just follow the notes. However, in addition to the 10 points from the related rates examples, I will replace one of your daily assignments with a free 100 if you guys can give me a paragraph in complete sentences summarizing this entire function. Meaning, if you can give me the summary, which I just kind of bulleted down here in complete sentences for this function, I will replace one of your homework assignments with a free 100. So the challenge is on. In terms of this one you will have to complete. Give it a shot, look at the key, and if it doesn't make sense on Thursday when we meet again, I will go through this one with you, because this one is crucial. You will see a lot of this on the AP exam, so it's very important that you guys know how to do this one. But give it a shot before I go through it with you. Alright?